All right, hello, welcome to the Unit 3 review video. I'm running short on time, so I can't give my usual spiel, but try all these problems on your own first, then check against the solutions key, try it again, then come back to the video, okay? The more you do on your own from your own brain, not from Miss B's brain, the better you will do on the test. So, let's take a look. Zoom in. Whoops. What's happening? There we go. Okay, give the scale factor from FG to F prime, G prime for each image, okay? We are always taking our new figure divided by our old figure. New divided by old, okay? Maybe your teacher has said image divided by pre-image, okay? Either way, I see that F prime, G prime is my new one, FG is the old. Let's my calculator going. So I'm going to take 18 divided by 12, which gives me 1.5. Okay, which makes sense, right? If I'm going from a smaller line to a bigger line, multiplying by 1.5 would make my side length bigger. Okay, versus this one. Okay, F prime G prime is the new one. So I'm going to take 8 divided by 12, which gives me 0.6 repeating. Okay. Again, that makes sense. Going from bigger to smaller, multiplying by 0.6 would make something smaller. Okay, this one, 12 divided by 12, hey, that's just 1, right? If I have a scale factor of 1, that means nothing changed. All right, triangle. P prime, Q prime, R prime is a dilation of triangle PQR using center C and scale factor 1.5. Every time you dilate, you need those two pieces of information. You need the center and the scale factor. Okay? Is triangle P prime, Q prime, R prime larger or smaller than triangle PQR? Well, if my scale factor is 1.5, I could test this in my calculator, okay? Any number, because they didn't give me any, I mean, they gave me numbers here. Any number in the whole world though, like 10 times 1.5 makes the number bigger, right? So it should be larger because my scale factor is bigger than 1. I'm using SF for scale factor. Is larger than 1. Okay, so what would the length of segment P prime Q prime be? Well, PQ is 5. So all I gotta do is take 5 times my scale factor. 7.5. Explain how you know. This is me showing my work. Anytime you type something into the calculator, you should be writing down like what you did. Okay. What must be true about segment MN? All right. There are a couple different things we can do here. First, we could figure out like what the length of that segment has to be, right? I am going to first look at this picture. How many triangles do you see in this picture? 2. I'm going to draw them. Draw the 2 separate. Okay, because it'll be easier to see my corresponding parts. So I have a small triangle and a big triangle. Right? So A and M and A, C, B. All right, I got my points all settled. Let's see, so this one has side length 1 and side length 1.8. Okay, CB is 6. And I know that 1 plus 2, so this whole side is 3. And I might have to break out my calculator for this one. 1.8 plus 3.6, 5.4 for this whole side. All right. So looking at these 2 triangles, I don't know if they're similar or not. Like based on this, I can't say for sure that they're similar. So let's try and gather some other information to see if they're similar. Well, I see that they both share angle A. All right. So there's one angle that's congruent, but I can't say anything else about those other angles. I don't have any parallel lines. I don't have anything. These are just two triangles. Okay. Well, I have one angle and I have two sides. Let me check the proportions of those two sides or the scale factors. Okay. So let's see here. I'm going to, well, since I marked that, I'm going to write that down. Okay. Angle A is congruent to angle A. Okay. 5.4 and 1.8 are corresponding sides. So 5.4, 1.8. Let's see what I get when I divide those. 3. Okay. Well, let's try again. 3 divided by 1 also gives me, whoa, not 1. 3. So I get the same scale factor for each pair of corresponding sides. So I can say triangle AMN is similar to triangle ABC by side angle side similarity. Okay, that was on your check-in. Right? One congruent angle and two sides with the same scale factor. Okay, so I know these are similar triangles. Awesome. What can I do with that? Well, if these are similar triangles, I should be able to find this missing side length, MN. Okay. Couple different ways to do this. I could set up a proportion. I could also know that I'm multiplying by 3 to go from here to here, so I can divide by 3 to go the other way. I'm going to do it the more complicated version. All right, so 3 and 1 go together. I'm going to use X. Anytime I have like a segment that I want to know the length, I'm going to label it with X because now I can pair 6 with X. Okay, I can cross multiply 3x. 3 times x is 3x. 1 times 6 is 6. Solve. X is 2. So that's one thing that must be true. What must be true about segment MN? MN must equal 2 units. Okay. The other thing I know is now that I've shown these are similar, I know they have congruent corresponding angles. Okay. Meaning, if this is equal and this is equal, hey, that must mean these lines have to be parallel, right? Usually, the paper will tell you these lines are parallel and you have to mark the angles. So this one's flipping it around a little bit. We know the angles are congruent, so those two lines must be parallel. So MN must be parallel to BC. So that's two different things that must be true. On the test, we would be more specific about which one we're looking for. Okay. All right. What shapes other than equilateral triangles and circles are all similar? Okay, let's think about what's special about an equilateral triangle. Let me switch back to my black pen. What's special about an equilateral triangle? Okay, it has all congruent angles and all congruent sides. So if I scale it up or scale it down, they will always be similar, the triangles, because I'll always have the same scale factor for every side. Okay? Think of another shape that has all equal sides and all equal angles. Square. Squares. Squares have all 90-degree angles and all 4 sides are the same, right? Okay. it wouldn't be enough to say a rectangle because, let me show you, look at my little screen over here. If I have two rectangles, one of them is like really long like this, and the other one is really short like this. Are those similar to each other? This and this? No. Okay, I have to have all congruent sides and all congruent angles. Okay. That is called a regular polygon. What's up?
This is for $4 more.
Okay, thank you.
Thank you so much.
That wasn't a teacher, so I wasn't gonna ask them to guest star in the video. Okay, regular polygon. Okay, that means that's exactly what I've been saying this whole time. That means all congruent sides and all congruent angles. I ran out of room to write the word angles. Okay, so just congruent sides are not enough. Just congruent angles are not enough. Cool? All right. Here is the image of triangle ABC and its dilation using center D and scale factor 2. Okay, so here's my center. Why is segment B prime C prime on the same line as segment BC? Okay. When we do dilations, I don't have a ruler handy, so I'm just gonna use this. When we do dilations, we want to mark along the same line. Okay, here's DC. So I would measure, multiply by 2 for my scale factor, and mark along that same line. Okay, so why is this on the same line? Well, because they were already on the same line to begin with, right? If these two were already on the same line and I dilate, C prime is not going to magically end up over here, right? So the word that we might use is collinear, which just means on the same line. Co like collaborate, linear like line. Okay, same line together. Okay, since B, C, and D. Okay, I know Mr. Geiger's key used the word collinear, so I'll write an alternate version without using that vocab word in case you forgot. So since B, C, and D are on the same line, they will stay on the same line after dilation. Okay, so this is basically what Mr. Geiger's key was saying, just without that word collinear. All right, how do you know that AC is parallel to A prime C prime? Okay, I'm extending those lines because sometimes it's easier to see parallel when I extend the lines. All right, well, what do I know about dilations? I know my side lengths change, but something stays the same. Oh, my angles. Angles stay the same when you dilate an image, dilate a shape. So let's start with that, because dilations, sometimes we say preserve, which means keep the same, like we're preserving the environment, trying to keep it. Because dilations preserve angle measures. Let's look. I know that ACB right here has to be congruent congruent to A prime, C prime, B prime. Those two angles have to be congruent, right? Because dilations preserve angle measures, angle ACB is congruent to angle A prime, C prime, B prime. Giving us, those are corresponding angles, right? If those angles are congruent, these lines are parallel, guaranteed. Giving us congruent, corresponding angles. All right. What relationship does angle C have with its corresponding angle C prime? They're congruent, right? Whenever we ask what relationship, it's either it's exactly the same or one's bigger than the other. Okay, they are congruent. Again, how do we know? Because dilations preserve angle measures. If you forget that word preserve, you could just say keep angles the same. Okay, like I'm using these words specifically because it's more concise, it's less to write out. But if you forget like one of these words, you can put it in your own words, right? All right. Lynn knows that angle A is congruent to angle D, okay? Marked. She claims that these triangles must be similar. Convince Lynn that the triangles are not similar. All right. One angle is not enough to show similar triangles. Okay? Every single pair of corresponding sides has to have the same scale factor. All right? So let's look. I'm going to pair these two longest sides together. So AC and DF. Okay? I'm going to take big over small. Big over small. Okay, so 19 divided by 10. Let's compare that to 13 divided by 7 and 8 divided by 4. All right, well, 19 divided by 10, pull out your calculators. 1.9, 1.86, and 2. Do we think these triangles are similar? No. Each side has a different scale factor. That's not similar. That's not similar. They haven't all been dilated by the same amount. Okay, so convince Lynn the three sides do not have the same scale factor. So triangle ABC is not similar to triangle DEF. You can be super dramatic and do a capital not as well. Not similar. All right, triangle BCD is similar to triangle FHE, right? At least 5 equivalent ratios based on the diagram. Okay, I saw a lot of people showing their answers in different ways here. Like in my key, I literally made a chain of 5 fractions that were all equal to each other. In Mr. Geiger's key, he did 5 pairs of equal fractions. Okay, that's what ratios means, by the way, this fraction. So let's do one together. Okay. Well, BC and FH, those are corresponding sides. So BC over FH has to be equal to, let's pick another pair of corresponding sides, DC and EH. Okay, so there's one. All right, we could also, so this was small triangle over big triangle. I could also flip that over and say FH over BC is equal to EH over DC. That's also true. Okay, any pair of corresponding sides, you can write them like this. I'm gonna write out like 5 of them that are all equivalent to each other. Okay, what am I doing? I'm gonna do big over small. Okay. So, like we just did here, FH and BC. EH and DC. Sorry, my brain was glitching. Okay, so it's these ones. Okay, I also have FG and BA. Okay, I also have AD and GE. I'm gonna do GE on top. Because all of my big triangles are on the top. All right, I also have GH and AC. Oops, my line was crooked. And finally, I could say FE and BD. Right? Do you know how to pair corresponding sides together like that? Okay. All right. For each image, determine if you have enough information to find the missing lengths. If so, find them. If not, explain why. Okay, DE is parallel to AC. I'm going to mark that. The little arrow. Parallel. Find the lengths of AC and AD. Okay. So again, I want to figure out how many triangles are in this picture. I see 2. So I'm going to draw those separated. They don't have to be really perfect and beautiful. Okay, I see DBE and ABC. All right, and let's label any side lengths that I know. So BD is 2, BE is 4, this is 5. 4 plus 6 for BC, so 10. And that's all I know here. All right. Do I have enough information to find these missing links? First off, let me label this as X and this as Y. Okay. To be able to find these missing lengths, I need to know for sure that my triangles are similar. So let's see. I have 3 options: angle, angle, side, 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 but I don't have all 3 sides here, so I'm going to cut that one out. I also have side, angle, side, like we did on the front, but again, I don't have 2 sides. So let's see if we can do angle, angle. Wait, both of these triangles have angle B. Okay, there's one angle. That parallel lines, that must be telling me something. Oh yeah, parallel lines give me congruent corresponding angles. Okay, so I know angle E and angle C have to be congruent. Okay, 2 angles, 2 congruent angles is enough to show they are similar. Okay, so you could write yourself a little note. I got angle, angle similarity here. So I do have enough information to proceed. All right, let's find AC first. So that's X. X pairs up with 5. Those are corresponding sides. So let's do X and 5. Okay. What is another pair of sides I can look for between these 2 triangles? I got X and 5. I could do Y and 2, but that's not helpful because then I have 2 different letters in here. Ew. Oh, 10 and 4. All right. So solve this in whatever way you know how. I'm going to say X times 4 is 4X. 5 times 10 is 50. dividing by 4, x is 12.5. Okay, make sure if you're using other letters that you label the segments so your teacher knows which side you're talking about. I called this X, so when I write X here, Miss Clyde or Miss Holstein or Mr. Geiger or Miss B will see, okay, well, there's X. If you want to be extra sure, you can even say AC equals 12.5. All right, let's see. Now I need to find Y. Okay, they're asking me about AD, which is this weird length. That's not like a whole side of a triangle, right? So let's find Y because then that'll help me find just that part. Okay, so Y goes with 2 and 10 goes with 4. Okay, same thing, solve. I get 4Y equals 20. So then Y is 5. Okay, meaning this whole side AB is 5. So if this is all 5 and I just want this part, well, 5 minus 2 will give me just that part. Okay, so AD is 5 minus 2. AD is 3. Okay, so you might have to find a longer side length and then subtract a known part to be able to find just that little part. Hopefully you organized your work better than mine because this is all messy. All right, MN is 6 units. Yep, that's on there. Find the lengths of N, Z, and XZ. Well, I've got one shared angle. I know this side's 5 and this is 10, but I don't have a second side to compare it to. I have 3, and I don't know how long that whole side is. So this has not enough information. Not enough info. We only have one congruent angle. And one pair of corresponding sides. I ran out of room, so I abbreviated. All right. Find the lengths of segments AB and BD. All right, how many triangles do you see here? 3. Let's separate them. We got a big one, a medium one, and a small one. I'm going to draw them all in the same orientation. All right. Let's do the big one first. What I like to do here, okay, I know my right angle is at B. Let's mark one of these angles to have 1 arc and the other to have 2. Okay, so now I know when I'm trying to arrange my triangles, the single arc will always be on top. And the double arc will always be to the left. Okay, so ABC. So let's look at my medium triangle here. My right angle is at D. And I see that A, within just this triangle, A has the single arc. So this is going to be A, which leaves B to be this other point. Okay, let's look at my small triangle. Okay, again, D is at the right angle. And the only other angle I have marked is C with this double line. Okay, so you see that, how I use that to stay organized. Double lines match, single lines match. Okay, let's fill in all the lengths we know. CB is 3. CD is 1.8. AD is 3.2. And I could add those together, 3.2 plus 1.8. AC gives me 5. Okay, they want me to find the lengths of segments AB and BD. So let me label AB with an X and BD with a Y. Okay, so AB is X, AB is X, BD is Y, BD is Y. All right, there are a bunch of different ways you could approach this problem because we have a lot of information to work with. Let's solve for X first, okay? Again, practice setting up these proportions. So I see X goes with 3. If I'm trying to solve for X, I definitely need one fraction that has X in it. So X and 3. And then, wait, I don't know if that's really enough. Oh, wait, no, X and 3. Yeah, I don't really have anything else in these two triangles. So I'm going to pivot. I'm not going to use these two triangles. I'm going to use these two. So let's do X and 5. X and 5 and 3.2 and X. Okay, you see how I pivoted there? I looked here and I saw X and 3, but then any other pair would add a new letter. I don't want two letters. I just want X, even if I have X in two different places. So instead of using these two triangles, I'm going to use these two because X and 5, 3.2 and X. All right, here we go. Cross multiply. X times X is X squared. 5 times 3.2 is, let me double check. 16. Okay, to get rid of a square, you take the square root. So X is 4. X is 4. And again, make sure you have it labeled so your teacher can clearly see if you're talking about X, which one are you talking about? All right, so let's find Y. There are a bunch of different ways you can find Y. Okay, I'm going to do just one way. If you end up with the same answer as me, congrats, your method worked too. So 1.8 and Y go together. Excuse me. Y and 3.2 go together. In both of these fractions, I took the small one over the medium one. Okay, so same thing, cross multiply. Y times Y is Y squared. 1.8 times 3.2 is 5.76. Notice how in my calculator, it doesn't go on forever, so I'm not going to round. I'm just going to keep 5.76. Okay, again, take the square root. 2.4. Okay, so if you had a different method and you got 2.4, congrats, you are a rock star. Okay, triangle ABC is similar to triangle A prime, B prime, C prime. Calculate the length of A prime, B prime. I'm gonna put an X right there because that's what they want me to find. All right, I don't have a side length to pair with X. Oh, if only there was a way that I could find a missing side length for a right triangle. Nice. 3 squared plus 4 squared here equals C squared, that missing side length. Okay, 3 squared plus 4 squared is 25. I just typed it in my calculator. Take the square root to get rid of my square. C is 5. All right, now I have a number I can pair with X. Nice. So again, let's set up our fractions. So 5 goes with X. And I could just pick 4 and 6. 4 goes with 6. Okay, again, cross multiply. X times 4 is 4X. 5 times 6 is 30. 30. Okay, 4 times X, so I gotta divide by 4. 30 divided by 4 is 7.5. All right. I'm going to pause recording this because it's 2:45 and I need to go to office hours. So pause and I'm coming back.
Yes.
Guest starring Aya. Does anyone know Aya?
Hi,
She's a senior.
guys.
She's awesome.
I am awesome.
All right, we are back. Well, I never left for you guys, but I just sat through office hours. All right, last page. Dilate triangle ABC using center C and scale factor 1/2. Okay, every time you describe a dilation, you need a center and a scale factor. Just like when we were rotating with a center, the center does not move. Okay, so that means whenever you're taking your ruler and you are measuring, the 0 should always be on the center. No matter what point that center is, your 0 should be on the center. Okay. So I'm going to do this in, I'm going to do this in 2 different ways, I think. One way I don't even need to use my ruler at all, actually, because I have these squares. Okay. So from C to B, that's 2 squares. Okay. If I cut 2 in half, 2 times a half is just 1 square. So there's B prime. Okay. If you want to use your ruler, always use centimeters because it's more accurate. Okay. I'm going to say that's 1.5-ish, 1.6. Okay, 1.6 times a half is, let me just make sure I'm not lying. Whoops. 1.6 times a half is 0.8, which would still be on that point. Okay, when we're dilating point by point. We're not worrying about the side lengths. We're literally just dilating points. Like the length, the distance from the center to each point. Okay, so this one, I might have to turn my paper upside down to measure because center should always be at 0. Okay, so it looks like I'm at 3.6, excuse me. So 3.6 times a half is 1.8. So I'm going to end up at 1.8, which is right there. So that would be my A prime. Notice I did not move my ruler at all. Okay, when you do your initial measurement, you keep your ruler in the same place when you're marking your new point. Okay, so to make my triangle, my new triangle, I'm just going to connect those up. I should use a straight edge. There we go. That's my new triangle. So this one, dilate triangle ABC using center D and scale factor 3. So center D. So every single point, move my computer, get more room. Every point, I need to place D at the 0 mark on my ruler. Okay, so from D to A, that looks like 1.2. Okay, and I'm using scale factor 3. So 1.2 times 3, 3.6. Keep your ruler in the same place. 3.6 is about here. Okay. If you're a little off, personally, I'm okay with that. Another way you can do this is see that, okay, from D to A, I went up 1 and over 2. So if I'm multiplying by 3, 1 times 3 is 3. So I should go up 3. 2 times 3 is 6. So I'm going to go over 6. 1, 2, 3, 4, 5, 6. Okay. I get about the same place when I'm at 3.6. Nice. There's A prime. 2 different ways to get the same point. All right. I am not measuring these side lengths. I'm measuring the distance from the center. Center is always 0 on your ruler. Okay, so from D to C, it looks like 1.7. So 1.7 times 3 for my scale factor, 5.1. I'll go over here. 5.1 looks like it put me right here. That's my C prime. Okay, from D to B. 1.2. 1.2 times 3 is 3.6, which would put me here. See that? Keeping my ruler in the same spot. There's B prime. Okay. Once I have all 3 points, now I can connect them up to make my triangle. Meow, meow. Meow. Yay! Okay, write a sequence of transformations that takes A, B, C, D to E, F, G, H. Let me grab some patty paper. Where's Miss Clyde keep this stuff? Oh, found it. Haha. Okay, so A, B, C, D to E, F, G, H. So this is my original one. I'm gonna trace it just in case. And I'm gonna include side lengths too. So this is 5, this is 4. Use my straight edge just to be super precise. I've been saying mega a lot lately. Mega precise. You're my student. Tell me, have you noticed that I've been saying mega a lot? I've been saying bro a lot. Does that happen to you guys? You just get like one word and then you just keep saying it all the time. Okay, anyway. Okay. We are always going in the order. Translate, rotate, reflect, dilate. Okay. So let's pick 2 points that correspond with each other to translate. So I think I'm gonna pick D and H. Right? That's kind of like the pointy one. So translate. I'm gonna say translate A, B, C, D. From D to H. All right, so now I'm here. Translate, rotate, reflect, dilate. So I'm going to rotate. Rotate, I need the center. Okay, rotate around center D, because that's the point that's lined up now. Rotate, rotate, A, B, C, D, around center D, until when? Okay, when should I stop rotating? Let's see. Say maybe there. Or there. Either way, let's go this way. So from here to here, I'm rotating around D until AD lines up with GH. Until AD lines up with GH. Hold on, I might be tripping. What? Why didn't I just do that? Until CD lines up with GH. Guys, I'm tripping. I had to trial and error a little bit. I know dilations preserve angle measures, so look, when I was playing around, AD, that seems kind of funky. But look, see how that angle perfectly lines up? So I need to revise this. I'm gonna go until CD lines up with GH, because now I'm perfectly lined up. Sometimes your first go at it isn't the right go. Got trial and error a little bit. Okay, so now the only thing left to do is dilate. I don't even need to reflect. dilate. Okay. Here is a tip. Use the test to take the test. Now, you may have heard that before, but what does that mean? I'm about to write a description of a dilation. Look back at other times we've told you how to dilate. Okay, dilate. Okay, looks like I named my shape. So let's say dilate ABCD using center. Okay, so what do I want for my center? I think I want D to be my center because it's the one that's not changing. So using center D, okay, and then they say and scale factor. Okay, so that's what I should do. And scale factor. Okay, let's see. Looks like this was 5 and 2.5. So I want my new one divided by the old. New, whoop, divided by old. 2.5 over 5. Type that in my calculator. You should get 0.5. I'm just double checking. Yeah. Which makes sense because it's smaller than 1 and I'm getting smaller. All right. Number 4, for each set of side lengths. Is this an acute triangle, right triangle, obtuse triangle, or impossible? The first thing we need to check, is this even possible to make a triangle with? Okay, I want you to imagine a triangle. Here's my 3 side lengths. 1, 2, and 50. Is it possible to make a triangle with one side being 50 and the other sides being 1 and 2? No, those 2 smaller sides are too short. Okay, so to check this, your 2 smaller sides have to add up to be bigger than your biggest side. Okay, so what do I mean by that? 9 plus 12. 21 is bigger than 15. Good. 1 plus 3. 4 is not bigger than 10. Impossible. Okay, 9 plus 12. That's bigger than 17, so we're good. Okay, pay attention. I'm talking about my 2 shorter sides here. So 9.6 plus 18. That's bigger than my longest side. Okay. So now, from here, to determine what kind of triangle you have, we are going to use the Pythagorean theorem. Okay? If this is true, I have a right triangle. All right? So let's test what's going on over here. Come down here and do A. So impossible because 1 plus 3 is smaller than 10. So 9, 12, and 15. 9 squared plus 12 squared. Is this equal to 15 squared? I like to put a question mark over that because I don't know that they're equal yet. Okay, so in my calculator, 9 squared plus 12 squared, 225, 15 squared, whoop, is 225. Okay, these are equal. That means that angle is so perfect, it is a right angle. This is a right triangle. Okay, let's try the next one. See, 9 squared plus 12 squared, is that equal to 17 squared? Okay, well, 9 squared plus 12 squared is 225. Wait, I already knew that. 17 squared is 289. Okay, that longest side is too big. So here, look at me for a second. If I have a perfect right angle, that means that this is perfectly equal. If that C is too long, what happens to my angle? It becomes obtuse. Obtuse. This is obtuse. Okay, if they were perfectly equal, I would have a right triangle, but C is too long. It's an obtuse angle. So D, okay, again, my 2 shorter sides, so 9.6 squared. Sometimes I just do parentheses for a decimal. Plus 18 squared. Does that equal 20.1 squared? Okay, so 9.6 squared plus 18 squared, 416.16. Okay, and then 20.1 squared is 404.01. Okay, again, if these were perfectly equal, I would have a perfect right angle. But that third side is too small, creating an acute angle. All right. Sorry this was a little late getting out, but if you subscribe, you don't have to wait for your teacher to post the link in Schoology. Subscribe and ring the bell so you're notified of every upload. Good luck tomorrow, guys. I know some of you are going to be out for the choir field trip. Be prepared to take your test on Monday when you come back if you are out for a field trip. Have a wonderful night. Good luck on your test. You're gonna rock it. Goodbye.